What specific problem does the new method, min LSTM and MNGRU, aim to solve, particularly in the context of existing recurrent models and their limitations?
The new methods, min LSTM and MNGRU, aim to solve the limitations of traditional recurrent models, specifically their sequential computation and reliance on backpropagation through time, BPTT, which hinder their scalability to long sequences. By removing hidden state dependencies from their gating mechanisms, min LSTM and MNGRU can be trained efficiently using the parallel scan algorithm, allowing for significant speedups in training, up to 235 times faster for a sequence length of 512 compared to traditional LSTMs. Additionally, these minimal versions eliminate the constraints on output range imposed by the hyperbolic tangent function, resulting in models that are not only parameter efficient but also capable of maintaining time-independent outputs. This addresses the computational inefficiencies of existing recurrent models, while achieving comparable performance to state-of-the-art sequence models like Mamba. Ultimately, min LSTM and MNGRU provide a more efficient alternative for sequence modeling tasks, particularly in low-resource settings where long sequences are common.
Can you explain how the proposed min LSTM and MNGRU work? Please illustrate the algorithm step by step, particularly focusing on how they achieve parallel training as opposed to traditional RNNs.
The proposed min LSTM and MNGRU models achieve parallel training by simplifying the traditional LSTM and GRU architectures through two main steps: removing hidden state dependencies and dropping range restrictions on candidate states. 1. Removing hidden state dependencies. In traditional GRUs and LSTMs, the gating mechanisms rely on previous hidden states, which prevents parallel computation. By eliminating these dependencies, MNGRU and min LSTM allow their gates to be computed solely based on the current input, enabling the use of the parallel scan algorithm for efficient training. 2. Dropping range restrictions. Traditional models use the hyperbolic tangent function to restrict the range of their hidden states, which can complicate training. By removing this restriction, MNGRU and min LSTM ensure that their outputs are time-independent in scale, further facilitating parallel computation. These modifications result in both models being trainable in parallel, achieving significant speedups. MNGRU is 175 times faster, and min LSTM is 235 times faster than their traditional counterparts, for a sequence length of 512 on a T4 GPU. This efficiency allows them to handle longer sequences effectively, contrasting with the linear training time required by traditional RNNs due to backpropagation through time.
Could you provide a simple yet illustrative example that explains how MNGRU processes a sequence of inputs? Walk us through the main steps of the algorithm using this example.
To illustrate how MNGRU processes a sequence of inputs, consider a simple sequence of three inputs, x_1, x_2, and x_3. The first step involves computing the update gate, z_t, for each input independently, using the formula z_t equals sigma text linear_d_h x_t. For example, for x_1, we compute z_1, and similarly for x_2 and x_3. Next, we calculate the candidate hidden state, ~h_t, without any dependence on previous hidden states using ~h_t equals text linear_d_h x_t. This means ~h_1, ~h_2, and ~h_3 are computed directly from x_1, x_2, and x_3 respectively. Finally, the hidden state, h_t, is updated using the formula h_t equals 1 z_t, o.h_t1 plus z_t o.h_t. However, since MNGRU does not maintain a previous hidden state dependency, we can initialize h_0 to 0 for the first input. For x_1, we compute h_1 equals z_1 o.h_1. For subsequent inputs, we use the previously computed hidden state, allowing the model to efficiently process the sequence in parallel, achieving significant speedups compared to traditional GRUs.
What are the primary theoretical or practical benefits of using MIN LSTM and MN GRU compared to traditional LSTMs and GRUs, specifically in terms of computational complexity and parameter efficiency?
The primary theoretical and practical benefits of using MIN LSTM and MN GRU compared to traditional LSTMs and GRUs lie in their computational complexity and parameter efficiency. Both MIN LSTM and MN GRU can be trained in parallel using the parallel scan algorithm, resulting in a training speedup of 175 times for MN GRU and 235 times for MIN LSTM on a sequence length of 512 compared to their traditional counterparts. In terms of parameter efficiency, MN GRU requires only O2D_HD_X parameters, which is significantly fewer than GRU's O3D_H, D_X plus D_H, while MIN LSTM uses O3D_HD_X parameters compared to LSTM's O4D_H, D_X plus D_H. This reduction in parameters allows MIN LSTMs and MN GRUs to use only 33%, 22%, 17%, or 13% of the parameters of GRU when varying the state expansion factor, leading to more efficient models that maintain competitive performance. Overall, these improvements enable MIN LSTMs and MN GRUs to scale effectively to longer sequences while being computationally less demanding.
How was the effectiveness of the proposed methods validated in the paper? Describe the validation process, including the datasets and metrics used to compare MIN LSTMs and MN GRUs with other models.
The effectiveness of the proposed methods, MIN LSTMs and MN GRUs, was validated through empirical performance comparisons across several tasks and datasets. Specifically, the paper evaluated these minimal models on the long-range, selective copying task, where they were compared against well-known recurrent sequence models like S4, H3, Hyena, and Mamba. The results indicated that MIN LSTMs and MN GRUs were capable of solving the selective copying task, achieving performance comparable to Mamba's S6 model, which was the only other model capable of solving this task. Additionally, the models were tested on MuJoCo locomotion tasks from the D4RL benchmark, where MIN LSTMs and MN GRUs outperformed Decision S4 and achieved competitive performance with Decision Transformer and Mamba. For language modeling, the models were trained on a character-level GPT using Shakespeare's works, where they achieved comparable test losses to Mamba and Transformers, demonstrating their efficiency and effectiveness across diverse tasks.
What specific results did MIN LSTM and MN GRU achieve in the experiments presented in the paper? How do these results underscore their performance in comparison to traditional models and recent sequence architectures?
In the experiments presented in the paper, MIN LSTM and MN GRU demonstrated significant efficiency and performance gains compared to traditional models like LSTMs and GRUs, as well as recent architectures such as Mamba. Specifically, MIN LSTM achieved a training speedup of 235 times and MN GRU a speedup of 175 times for a sequence length of 512 on a T4 GPU, with even greater improvements for longer sequences, 1324 times and 1361 times faster for a length of 4096 respectively. In terms of empirical performance, both MIN LSTM and MN GRU successfully solved the challenging selective copying task, achieving comparable results to Mamba S6 and outperforming other baselines like S4, H3, and Hyena. Additionally, in language modeling tasks, MIN LSTM and MN GRU achieved test losses of 1,555 and 1,548 respectively, which were on par with Mamba and Transformers, but required significantly fewer training steps. These results underscore that the minimal versions not only retain competitive performance, but also excel in training efficiency, making them viable alternatives to both traditional RNNs and modern sequence models.